All right, functions, today we came back and this is what we worked on. So what I would like you to do is hit pause. I would like you to practice these warm-up problems. These are things that are going to come up throughout this entire unit. Okay, so hopefully when you were doing these, you saw that the first one was a difference of two cubes. So this would be your final answer. Make sure that you did that. This was a GCF, and then you needed to do box and diamond because you ended up with a trinomial. And this was, you ended up with doing the box for factor by grouping, and then there was a difference of squares. So hopefully you got that. Okay, so we are starting a new unit. It's called rationals. When you think of rational expressions and functions, we're going to be multiplying and dividing. But first, we need to define what a rational expression is. We need to be able to describe their domains. So in this unit, it's going to be all real numbers. That's always going to be the beginning, but then it's going to have some kind of restriction. Not always, but most of the time there's going to be some kind of restriction, and we're going to go over that. You're going to simplify, so you're going to write those rational expressions in its lowest possible terms. And we'll multiply, and then we're going to divide, which is finding the reciprocal and then multiplying by that, which is division. Keep, change, flip, you may remember. So in the last year in Algebra 2, you did a lot of this. So most of this is progressing. In fact, everything on this side is in the progressing level. Simplifying, multiplying, dividing. Adding and subtracting is a lot harder, and that is what we will be doing in meeting. And then in advance, we'll be doing like a complex fraction kind of thing, which takes everything and puts it all in one problem, which is not anything you need to really practice, but we'll go over it. Okay, so we're going to define it. So honestly, in your notes, what you need to write down as a rational expression is called an algebraic fraction. It really could be any one of these. Here's a list of examples. We've got x over y. We've got negative a over 4. We've got two binomials, so n plus 4 over n plus 2. We've got two polynomials, so 8x squared minus 2x plus 5 divided by 4x squared plus 5x. And then x to the fifth could also be a rational expression because we could just put it over 1 and make it into a fraction. So really that's all we're doing. We're just taking algebraic expressions. So it's an algebraic expression over an algebraic expression, or a number over an algebraic expression, or an algebraic expression over a number. There's lots of different ways that this can be done. It's pretty much anything. So we are going to start with finding the domain. Okay, so the domain. The domain is always going to be all real numbers except for whatever value in the denominator makes it 0. Because just like we've learned before, we can have a number in the denominator and we can have 0 in the numerator, but we can never have 0 in the denominator. So friends, don't let friends divide by 0. Maybe someday when you're bored, ask Siri to divide by 0. Do 0 divided by 0 and see what happens. It's kind of a funny little shtick. So anyway, I'm going to go through a very simple example. So the first thing we want to do is we're going to take this f of x is equal to 1 over x, which is a standard rational expression. We've got a number in the numerator and a variable in the denominator. We are going to set that denominator not equal to 0 because we don't want it to equal 0, but we're going to treat it like it's done the exact same way, but we're finding the values that will make it 0 so that we can't, because we don't want it to be equal to 0 because that's going to create a vertical asymptote. So x is not equal to 0. So I took the denominator, set it not equal to 0. There's nothing left for me to do. X is by itself, so I'm done. Then I'm going to state the domain. So this is the domain. This is how it's going to look when you do the domain in your homework. This is one of like 4 or 5 ways that I'm going to show you that you can state the domain. In your homework, it's going to look like this. This is called set notation. They're going to give you curly brackets, and this is going to be all values of x. This bar is such that x does not equal 0. So that says all real numbers except x can't equal 0. Another way that will look is like this. This is the way that I typically do it. I do a bold R, so it's all real numbers except x cannot equal 0. This one says the same thing. It's all real numbers except x cannot equal 0. And then you could just write it out. All real numbers, x cannot equal 0. So those are the different ways. We will use them interchangeably. On the test, you can choose the way that you want to do it. I just need to make sure you know how to read all of them so that when they're given to you in different options in your homework, you can do all of that. So we are going to define rational expressions and rational functions that describe their domains. So a function is defined by a quotient of polynomials. It's called a rational function, and it has the form of f of x is equal to a function over another function where the function in the denominator cannot equal 0. So if we take this very simple function, 2 over x minus 5, this whole thing cannot ever equal 0. So we cannot have a value of x that would equal 0. That's going to be that vertical asymptote that we've seen in the graph. So the domain of the rational function consists of all real numbers except whatever's going to make that denominator equal to 0. So what we'll do is we'll say x minus 5 is not equal to 0. So here, let me see if I can write that. So let's see, where am I? So x minus 5 cannot equal 0. So we're going to add 5 to both sides. And we get x cannot equal positive 5. And that is because a positive 5 would make that function 0. 5 minus 5 is 0, and we can't have that. That's undefined. So we will not, that's what we're doing. So we're going to go through this example. So the first step that we want to do is we don't really need to worry about the numerator right now when we're just talking about the domain. The domain goes with the denominator, d. So domain and denominator. So we are going to figure out, first we have to set this denominator equal to 0, or not equal to 0, excuse me. So x squared minus x minus 6 is not equal to 0. Well, to figure out the values of x that are going to make it work, we have to do something. And here comes my second favorite phrase. Whenever you're in doubt, factor it out. So it looks like we have a trinomial here, and we can factor that. The factors of negative 6, x squared that add up to a negative 1 are negative 3 and positive 2. So we're going to end up with x plus 2 times x minus 3 is not equal to 0. So we factor that out. And now we solve it just like we would solve it if we were looking for the x-intercepts. So we would solve that by setting each factor not equal to 0 and solving. So we get x plus 2 is not equal to 0, or x minus 3 is not equal to 0. And then we end up with x cannot equal negative 2, and x cannot equal positive 3. And so our final answer for the domain are all values of x, all real values, such that x cannot equal negative 2 or 3. So again, the first thing we're going to do here is we're going to set the denominator not equal to 0. So 5 does not equal 0. Well, is that true? It is true. 5 does not equal 0. We can't do anything to 5 to make it 0. So therefore, the answer to this, the domain, is all real numbers. This is just a line. We've got a slope of 2 over 5. So it's going up to over 5. And then we've got a y-intercept of 3 over 5. So this is just straight up a line. Okay. So what I would like you to do is I would like you to take a few minutes, hit pause, and I would like you to state the domain for all of these functions. Okay, so hopefully what you did is you started with setting 6 not equal to 0. 6 does not equal 0. So then we end up with all real numbers. You could have put negative infinity to infinity, but it is all real numbers. This is just a line. This one, we have to take the x plus 2 and set it not equal to 0. And so then we end up with all real numbers such that x does not equal negative 2. Because if we subtract 2 from both sides, we get x does not equal negative 2. This one was a little more complicated. We needed to set the denominator x squared minus 9 not equal to 0. That does factor. So we get x plus 3 times x minus 3 is not equal to 0. We set each factor not equal to 0 and solve. And so we end up with all real numbers such that x does not equal plus or minus 3. You could have put in positive 3 and negative 3. This is just a little bit of more shorthand, and as I've said before, I'm always going to take the lazy way out and write it as short as possible. So if you have any questions, let me know. This is where we ended today in class, and I will see you all tomorrow. We are going to start class by taking notes and simplifying. So I hope you all have a great day, and I'll see you tomorrow.